class. Today we're going to get close to the end of topic 2.1. We'll finish it up on Monday and jump in right into topic 2.2. As a reminder, make sure you're doing that chapter 1 self-study. It is going to be on the first test. And your personalized lab Achieve link is now available on OWL under grades. So go there, click on your Achieve link, use the code at the back of your lab manual along with your UWO emails, and you can sign up for Achieve. So, question to get started, am I ready for the lab? I've signed up on Achieve with my personalized link. I have my lab manual. Do I look like I'm ready to have my first experiment? Anybody want to tell me yay or nay and what's wrong?
You don't have your goggles.
I don't have my safety glasses. There we go. Okay, so here are my safety glasses. With your 1301A lab manual, you actually get a free pair of safety glasses. They're included with the lab manual, but you actually have to pick them up from the Chem Club just outside of the first year Chem labs. Okay, so I have my safety glasses. I have my lab coat. Am I ready for the lab? What's wrong? Pardon?
Button up the lab coat.
That's right. Common oops. People post this on social media. They're like, oh, cool, look, I'm a scientist. But they forget to do up their lab coat. You always have to do up your lab coat in the lab. Okay, so what else? Am I all good to go now? Yes.
You have to have your hair up.
There we go. If you can tie your hair back in a ponytail, it means you should. Or however you want to tie it back. Okay, so I have my hair tied back. I have my lab coat. How am I doing?
I can see your ankles.
You can. Yes, my socks are below my ankles and my pants are rolled up. Good thing I can just roll my pants down. I did not wear shorts. And my socks are nice and long. They can go above my ankles. Your socks have to go above your ankles. Your pants have to go to your ankles. Okay, so shorts, Crocs, open foot shoes don't work. Okay, how are we doing? Thumbs up. Do I look ready for the lab? Any other concerns? Okay, I think I'm pretty good to go as well. I have my lab coat, my closed-toed shoes. Oh, my thing is still rolled up, but that's nice and easy. I can unroll this. Make sure that we have shoulder to toe coverage and wearing our safety glasses. And now I'm excited. I get to go to my first lab. I want to make sure I pick up my safety glasses well ahead of my first lab. You go to course info. Right here, Chem Club, pick up your safety glasses. You can find the schedule and make sure you pick that up. How do you get to your lab? Well, hands up, who has found the first year Chem labs already? Awesome. If you haven't, you can follow me after class and we can walk over there. On OWL, under labs, there are 2 videos that show you how to get to the lab. If you follow the videos, it's nice and easy. It is a little bit tricky the first time because you have to get to the chemistry building, and then from the chemistry building, you get into the material science edition, the MSA, and that's where your labs are. Once you do it once, you're good to go, but I wouldn't wait till like 2 minutes before your first lab to try to find it. So walk over there today so you're ready for next week or the week after. Okay, so I said you have your first lab or your Achieve link posted on OWL. This also includes, in another column on OWL, your lab location. So it's going to say Material Science Edition 1220 or whatever room, or Chemistry Building 110. And then it's going to give you a zone if you have an MSA building number. So zone A or B or C or D or E. So when you walk into the lab, there's going to be a big letter on top of the door. So walk in zone A or zone D, whatever you're assigned to. That makes sure you're just in the right region of the lab with your teaching assistant and your fellow classmates. Okay, question. This is an iClicker question. Chat with the person beside you. Which of the following are included in your lab submission? And 10 more seconds. And 3, 2, and 1. Okay, 96%. Very well done. A nice leading question. We definitely want to make sure we do that pre-lab on Achieve. It opens up, I think, the Friday before the lab, so it should be open today. Submit in the lab sheet so you don't walk away with it. And then afterwards, you upload your data and your observations and fill out the SMART worksheet, fill in the blank online, Achieve submission. And then you have completed your lab. And we hope you have a really great experience in the lab. Okay, let's jump back to topic 2.1. We have learned about orbitals and how these wave functions for the orbitals describe, if we square it, the probability of finding an electron in that region. We can figure out the energy, the relative energy of these orbitals and their shapes, and figuring out where these electrons are, what orbitals they're in, how we can describe these electrons. That helps us to know how atoms react with one another, what these atoms are going to do. So we want to know how to write out electron configurations, assigning electrons to those orbitals. We start at the lowest energy orbitals and we work our way up. Now, last class, I showed you a strategy for using our periodic table to write out an electron configuration. So we're going to just quickly review oxygen and jump back into bromine. Here we have our S block, our P block, our D block, and our F block. When I get my periodic table on a test or something like that, or when I'm doing homework, I identify these different regions of the periodic table, and then I count 1, 2, 3, and 4. S starts at 1. P starts at 2. There is no 1P, but it does start at 2P. D starts at 3. F starts at 4. So when I look at S, the first row with hydrogen and helium, I can count those electrons in the 1s block. And then there's the 2s, 3s, 4s, and so on as we go down the periodic table. So when we're wanting to write out the electron configuration for oxygen, as we did at the end of last class, oxygen we can see has an atomic number of 8. So that means it has 8 protons. If it's neutral, we're going to see later in class how we can change the charge. But if it's neutral, that means it also needs to have 8 electrons. So I need to take these 8 electrons and assign them to orbitals. I start at the lowest energy and I work my way up. Now, maybe you've memorized the order of the orbitals. That's great. If you don't like memorizing stuff, you can use your periodic table to read out what these orbitals are. So I want to count all the way to oxygen. I'm starting in the hydrogen spot. That means a 1s orbital. And I'm going to count helium, we can imagine, is over there. So 1, 2 electrons into my 1s orbital. There is no 1p, so then I jump down to 2s. In the 2s orbital, we can have an electron with an upspin and a downspin. So 2 electrons there. And then I hit my 2p block, and I'm going to count across 1, 2, 3, 4 electrons in my 2p orbitals. Okay, so let's now jump on to our bromine. This one's a little bit more interesting. Bromine, first thing we want to do is find it on the periodic table. The atomic number for bromine is 35. So I need to assign 35 electrons to this neutral atom. So I'm going to start at the beginning of the periodic table again, starting with my 1s spot. I have my periodic table here as well. For bromine, we're going to count across. So we start at 1s. We can fit 2 electrons there. Then I jump down from 1s to 2s, and I can fit 2 electrons there. After 2s comes 2p. How many electrons can we fit in 2p? 1, 2, 3, 4, 5, 6. That makes sense because we have px, py, pz, 3 degenerate orbitals. Each can fit 2 electrons, so 2, 4, 6. Then we're down to 10 electrons that we've added so far. Now I need to jump over here to add my 11th electron, but I've forgotten where I left off, so I'm going to count. This is the s block, these 2 rows, 1s, 2s, 3s. So that's where we are. 3s, 2 electrons in there. And then I jump over here. Oh, I've forgotten where I was again. So S starts with 1, P starts with 2, D starts with 3, F starts with 4. So this is 2P. So what row are we in now? 3P. And where were we going? Bromine. We still have a ways to go. 1, 2, 3, 4, 5, 6. 6 electrons there. We jump down. Now we're in the 4s block. We can fit 2 electrons there. Now we're not in the 4D. Where are we? 3D. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons in my D. Remember last class we learned there are 5 3D orbitals. dxy, dxz, dyz, dz squared, and dx squared minus y squared. So 5, each hold 2 electrons, that gives us 10. That's why we count across 10 spots. Now, oh, I've forgotten where I am again. 2p starts here. So this was 2p, 3p, 4p. So I'm in the 4p orbital. 1, 2, 3, 4, 5. 5 electrons there. Okay, so let's write that out. 1s, 2, 2s, 2, 2p, 6, 3s, 2, 3p, 6, 4s, 2, 3d, 10, and 4p, 5. We can count all those up. As long as I wrote it out correctly, that brings us to 35 electrons. Now, I'm often asked about the order for 4s2 versus 3d10. Who wrote it using this filling order in high school? Okay. Who wrote it the way where you group all principal quantum numbers together? Okay. There are 2 valid ways to do this. I've just shown you the filling order as we go across based on energy as we're filling up. That's what makes sense for me. That's the way I write it as I go across the periodic table. So that's my preferred method. But an equally valid method is to then group it by principal quantum number. So then you could say 3s2, 3p6, 3d10, and then move to 4s2. You can group it afterwards. The important thing is to remember the proper energy levels, that we're filling the 4s2 before we fill the 3d10, and that's important. But if you want to group it by principal quantum number afterwards, that's perfectly fine. Any questions on writing out this electron configuration? Yes?
So don't we probably figure out what does the get to go before us? Because there are like some exceptions.
Great question. So how do we figure out when 3D goes before 4S? I'm going to jump to a new slide. 1, 2, 3, 4, S, P, D, and F. Okay, as we move into the transition metal region, that's the D block here, we do start to have some exceptions. We're not going to talk about exceptions quite yet. Give it a couple more weeks, and we'll talk about 2 exceptions that you need to know for our course. But as you get into that transition metal block, it does get a little more interesting because there are some exceptions. Real life, real matter does do what it wants to do. And so sometimes we could find for some of these elements, it might not follow our filling rules because another reason comes into play, like half filling all the orbitals versus fully filling lower level orbitals. But we don't have to worry about that quite yet. One thing I do want to mention here that I didn't mention last class are the lanthanides and actinides. Do you see where we have the 58, the cesium there? That kind of jumps in right between 57 atomic number lithium and 72. So we've kind of tucked in this entire F block into that zigzag part of the periodic table. We go from 57 to 58, and then all the way to 71, and then 71 back to 72. A more accurate way to draw this periodic table is to make it extra long and to tuck that F block, the anthonides and actinides, into the periodic table. But it doesn't fit on an 8.5 by 11 sheet very nicely. So we've opted to kind of pull that out, stick it at the bottom, but we know it belongs in there. So a common question is, well, how do we write electron configurations with F orbitals? Well, when we get into the F block, we do have many exceptions. Some of them follow the rules and a few of them start to do some funny stuff. So for cesium, for 58, for example, we could say, if we started at cesium here, or cerium, sorry, I said the wrong thing. So if we started at 55, we're at 1, 2, 3, 4, 5, 6 S, fit 2 electrons there, so 1 and 2. And then we jump down to 4 F. Sorry, we jump into 3, 4, 5 D, put 1 electron there, then jump to 4F and fill that up. And then we go back to the 5D and fill that up. That's true for 58. When we get to 59, there's an exception. So we're not going to worry about it too much. That said, when we get past the D block, if we were doing an element like iodine, 53 over there in the halogen region, that's a terrible example. Let's jump down 1 row. 85, AT. 85 comes after the 58 to 71. So by the time we get to 85 electrons in our electron configuration, we have gone through the F block, and then it's kind of locked in. So to get to AT, 85, we would do 6s2, 4f, 14, and then go back to 5d10, and then continue along. So if we're past the F block, we just put that whole thing in, 4f14. We can fit 14 electrons in there because there's 7 F orbitals. Thumbs up if that kind of makes sense. Okay, so we're not going to be trying to trick you on the exceptions at this point, but if we've gone past the F block, make sure you include that in the description. Okay, let's keep moving along here. Okay, we can find patterns, and I'm sure you're already seeing lots of patterns. The periodic table is periodic. It has these recurring themes and patterns in it. As we go down the periodic table, we can see some important patterns happen. Let's look at the group 1 elements. Group 1 elements are right here: hydrogen, lithium, sodium, potassium. All of these electron configurations end with 1 electron in an s orbital. Hydrogen finishes with 1s1 electron. Lithium, 2s1. So 1 electron in the 2s orbital. 1 electron in the 3s orbital. Do you want to guess what this one finishes with? 1 electron in the 4s orbital. As you go down, those are the valence electrons. We could go to the next group, the alkaline earth metals. Beryllium, magnesium, calcium. They all end with 2s2, 3s2, 4s2, 5s2. And you can see the pattern as we go down. If we went over to the halogens, group 17 here. I'll circle this one over here in our notes. It all has whatever number, principal quantum number, s2, and then 5 electrons in the p. So 2s2, 2p5, or 3s2, 3p5, 4s2, 4p5. And it has that same pattern. All of these elements have 5 p electrons in the outermost shell. So it's nice and easy to figure out electron configurations and patterns based on using the periodic table. Based on the number of valence electrons, the electrons in these outer shells, this also tells us how elements react. A lot of these elements here tend to react in a way that give them one more electron to have filled p orbitals. So that it'd be 2p6 if it gained an electron, 3p6 if it gained an electron. So we can look at these patterns as we go down the periodic table. Okay, as we're writing out these electron configurations, you can see that sometimes the annotation gets really long. For example, iodine, we were just looking at that one right here, 53. That is a lot. I'm not even going to read it out. 1s2, 2s2, all the way up to 5p5. It gets really long. It gets really tedious. And if you try to write out the electron configurations for all the elements in the periodic table, you would be repeating yourself over and over and over and over again as you go along. So to make life simpler, scientists like to make things simple sometimes, which is wonderful. We can say, you know what, I don't want to have to write out this full electron configuration. What I'm going to do is count backwards to the last noble gas. So I'm at atomic number 53. I'm going to go back 52, 51, all the way back and find the most recent noble gas, which is krypton. And I'm going to say, you know what? The entire electron configuration of krypton, you know what it is. You can look it up on the periodic table. Put that in square brackets, the most recent noble gas that you passed, and then just write out the electrons that you've added since then. To get from krypton, the most recent noble gas, to iodine, what do we have to do? Well, I'm going to go across. We have to fill up this orbital, this s orbital. Which one is it? 1, 2, 3, 4, 5. I'm losing track now where I was. 1, 2, 3, 4, 5. So 5s2, 4d10, 2, 3, 4, 5p5. Yay, that's how we got there. And we saved ourselves some muscle cramps in our fingers for not writing out the whole thing. So just look at the most recent noble gas and write out what's happened since then. Question, yes?
For noble gases themselves, would you just put like a square bracket in the element?
So the question is, how do we identify the noble gas? Use its symbol and put square brackets around it. Yes.
So for the electron configuration of a noble gas, would you just like put the symbol itself, or would you have to write it out?
So what if you were writing out the electron configuration for krypton? It depends. I would accept either way. So krypton with square brackets, or you could write out the whole thing. I would probably just write out krypton with square brackets. But I mean, you could write it out another way. So you could say argon and then add the stuff since. As long as you're communicating the right number of electrons, that's fine. Question, yes? The note in mine says 5p6. Does yours say 5p5? I think it was corrected in your version, right? Okay, it's supposed to be 5p5. It doesn't have 6 electrons. That was a typo in my notes from last year. Okay, so let's keep jumping along here. We have these abbreviated electron configurations. And as a science student, you need to know how to do both. You need to know how to write out the full electron configuration and how to use and interpret the abbreviated electron configuration. So let's do some practice. We're going to do some abbreviated electron configurations now, and we're going to start with cobalt. First challenge, where's cobalt on the periodic table? Look at the back of your workbook. You have a periodic table there. Can someone shout out the atomic number for cobalt? Pardon? 27. Okay, so we have to find 27 on our periodic table. There is cobalt. So it's in the middle of the transition elements, the middle of the D block here. So that means we have 27 protons in cobalt. If it's neutral, that also means we need to assign 27 electrons. So we could start with 1s2, 2s2, 2p6, blah, blah, blah. Or we could say, I'm going to look back and find the most recent noble gas. The most recent one that we passed is argon. So if I want to write the abbreviated electron configuration, I can say we just passed argon. You know what that means. And what's happened since? Well, 1, 2, 3, 4 S, count 2 electrons over, and then 3D, 1, 2, 3, 4, 5, 6, 7. Okay, nice and simple. Saved a lot of time and effort. Now let's look for barium. What's the atomic number of barium? Who can find it on their periodic table? 56. Indeed. That's a lot of electrons to place, but we're going to make our life easier and look to see what most recent noble gas we just passed, which is xenon. Since xenon, we just need to add electrons into the 6s orbital. We count across 1, 2. 2 electrons in the 6s orbital. Okay, so your turn. What about that last element, tellurium? What is the abbreviated electron configuration for this element? Work with the person beside you and submit your answer. And 10 more seconds. And 3, 2, and 1. Okay, 94% going for C, and I agree. That means we passed krypton as our most recent noble gas. We added electrons in the 5s block. We counted 10 across for the 4Ds, and then we counted 1, 2, 3, 4 electrons in the 5p orbitals. Excellent. Let's keep moving along. So far, we've been looking at neutral atoms and their electron configurations. We want to move to ions, but before we do that, we need to define what are core electrons and what are valence electrons. The rule to remember here is that valence electrons have the highest principal quantum number. So you look at all the electrons with different principal quantum numbers, find the highest n, and count up the electrons that have the highest n. Those are our outer electrons. Those are the ones that participate in bonding. So those are the ones that become really important to know. What are the core electrons? Well, everything else. Everything that is not a valence electron. The core electrons, once those orbitals are filled, they kind of get like locked in and drawn very closely to the nucleus of the atom. So they don't participate in bonding. So let's look at the electron configurations for oxygen and bromine, which we did at the beginning of class, and identify the core and the valence electrons. So for oxygen, we can see we have principal quantum number 2 as the highest principal quantum number. We have 2s and 2p electrons. We have a total of 6 valence electrons in oxygen. 4 plus 2 is 6, which means we have 2 4 electrons. For bromine, it's a little more interesting. Again, we find the highest principal quantum number, 4, and that means 5 plus 2 is 7. This one has 7 valence electrons, which means all these other ones, along with those 3 Ds, are the core electrons. Jumping over to my paper periodic table here. Better. Okay, for oxygen, it's in the P block of the periodic table. Here's our S block, here's our P block. When we talk about the S block and the P block, those are our main group elements. And we can count how many valence electrons are in these main group elements based on where they are on the periodic table. So we just looked at oxygen. Let's count across. 1, 2, 3, 4, 5, 6 valence electrons. Sulfur also has 6. Selenium, you want to guess? 6. Okay, we were looking at bromine. We're going to skip the D block because that's not the highest principal quantum number. So we go 4s and 4p. 1, 2, 3, 4, 5, 6, 7. It's 1 away from having a noble gas electron configuration, from having a filled octet. So for the main group elements, it's nice and easy to count the number of valence electrons based on their place on the periodic table. When we look at the transition metal elements, it gets a little bit trickier, which means it's beyond the scope of our course. Sometimes for the transition metal elements, the S and the D electrons are considered valence because they can all participate in bonding. Sometimes they don't, and some of them are core and some of them are valence. Okay, so when we're counting valence electrons, we're going to be focusing on the main group elements, the P block and the S block, and we're just looking for the highest principal quantum number. Okay, so far we've just done neutral atoms. Now we need to move along to ions. Lots of matter around us, table salt, minerals, they're made up of ions. So as a reminder, cations are the positively charged ions, anions are the negatively charged ions. Now, how do ions form? Who says to get cations, we add protons? Who says we remove electrons? That's right. What happens if we add protons? Yes, what happens? That's correct. The element completely changes. The identity of that element is no longer sodium if we add a cation. It's whatever element is next in your periodic table, right? So we can't be adding and removing protons, but what we do, and what actually happens in real life, is that we add and remove electrons. So if we want to make a positively charged species, and the number of cations in the nucleus is fixed, well, how can we change the ratio of positive to negative particles? Well, we have to remove an electron to make that happen. Number of protons is constant. If we want to have more protons than electrons, we just have to remove some of the electrons. So cations, we remove electrons. Anions, we add electrons. Now, the way that we do that is very important. For cations, make a big star in your notes. Those electrons are removed from the highest principal quantum number level. Not necessarily the orbital that you just added electrons to when you were writing out the electron configuration. It's removed from the highest principal quantum number orbital. If they're the same, then choose the one with the highest energy. So the highest N level. So for example, sodium, I'm going to find this on our periodic table. It has a valence electron in 3s orbital. So it has a 3s1 configuration there. So 1s2, 2s2, 2p6, 3s1. If we want it to become sodium plus, the cation, we have to remove an electron. Based on its configuration here, the 3s electron is the highest energy electron. So we remove that highest principal quantum number electron. We're left with just what was the core electrons, and that electron goes bye-bye and is usually transferred to another element, which becomes an anion. If we're adding electrons, well, just continue following your orbital filling rules and add it to the next available orbital. Okay, so let's do some practice here. Write out the ground state electron configurations for O2 negative, so oxide, fluoride, sodium plus, and magnesium 2 plus. When we're writing out electron configurations for ions, I strongly encourage you to start with the neutral atom. So I'm going to quickly write out the electron configurations for these because this is old news now. We know how to do this. So a neutral oxygen is 1s2, 2s2, 2p4. Well, if I want to change that to be oxide, what am I going to have to do here? Hands up if we remove electrons. Hands up if we add electrons. Yes, we need to add them so that we have more negative charges. How many electrons do we add? Well, we look at the charge and see what the difference is. We're going from neutral, so that means same number of protons and electrons, to 2 negative. That means 2 more electrons than the number of protons. Oxygen on our periodic table has an atomic number of 8. When it's neutral, it has 8 electrons. We need it to have 10 electrons to be O2 negative. So we're going to add those 2 electrons to the next available spot. We have currently 4 electrons in the 2p orbitals. We can add 2 more to the 2p orbitals to make that 6. So 1s2, 2s2, 2p6. On our periodic table, we start with the electron configuration of oxygen, and we want to add 2 more electrons. 1, 2. It doesn't turn it into neon. We're just imagining that we're adding electrons here. But you can see it now has a noble gas electron configuration, kind of like neon. Well, exactly like neon. Okay, let's do fluorine now. Writing out its regular neutral electron configuration, 1s2, 2s2, 2p5. If we want to make it fluoride, we're going to have to add how many electrons? Show me with your fingers. Agreed. 1 electron to give it 1 extra negative charge. Where do we put it? Well, in the next available spot, we have 1 space in the p orbitals. We'll add it there. 1s2, 2s2, 2p6. Good. Okay, now let's move to sodium. I'm going to write out the full electron configuration. 1s2, 2s2, 2p6, 3s1. But now I want to turn this into sodium plus. Where do I remove the electron from? Who votes for 2p6? Who votes from 3s? And I agree, 3s. That's the highest principal quantum number. We're going to steal that electron away. That's the one that we can reach most easily. So we keep those core electrons, 1s2, 2s2, 2p6, but that 3s1 electron is now gone. Okay, magnesium. We'll start with the neutral version, 1s2, 2s2, 2p6, 3s2. Well, if we want to make magnesium 2 plus, show me with your fingers, how many electrons are we dealing with here? 2. Are we going to add them or remove them? Remove them, that's right. So then we have more protons than electrons. Where do we want to steal them from? Highest N value. That means we're going to steal them from the 3s2. Okay, hands up. Who notices a pattern on the screen on the right-hand side. Okay? Do you see how all of those electron configurations are the same? All of them have the same noble gas electron configuration. And if I still had this up on the screen, it would match neon. These species are all four of the ones we did plus neon, these are isoelectronic. What does that mean? Well, an isosceles triangle has two sides that are the same, so it means the same. An isoelectronic, continuing with that prefix and the root, it means we have the same number of electrons in the species. It also means that they're in the same orbitals. If they're in different orbitals, they're not isoelectronic. But we saw on the last slide, all of those species, cations, anions, neutral atoms, had the same electron configuration. So my question for you, chat with the person beside you, which of these ions or atoms is isoelectronic with chloride, Cl negative? And 10 more seconds. And 3, 2, and 1. Well done. Okay, many people went for C, which is calcium 2+. Using my periodic table, I started with chlorine. I added an electron. Chloride with the extra electron is isoelectronic with argon. So those species are isoelectronic, but argon wasn't one of the options. Neon was, but not many of you fell for that. That's the wrong noble gas. Well, if we look at calcium, it's over here. If it loses 2 electrons, we count backwards 2 places. 1, 2, which is where we counted forward 2 with chloride. So those species are isoelectronic. Same electron counts in the same orbitals. Okay, let's finish up with this example now. There's actually nothing new for me to share with you, but we're now going to apply this to the transition metals. Because it gets a little bit more interesting, we have to think a little more carefully, but the rules are the same. Make sure we're removing those electrons from the highest principal quantum number when we can. Okay, so let's write out the ground state electron configurations, and we're going to start with vanadium. So I'm going to start out with the neutral atom and then turn it into an ion. So I look on my periodic table. I see the most recent noble gas is argon. Make my life simple. I'm going to start there and add to that. So 4s2, 3d3. Well, I want to turn this into V3+, the vanadium cation. We're going to vote on where to pull these 3 electrons from. I need to steal 3 electrons away so that it turns into a +3. Who votes that I take away those 3d electrons, those 3? We added them most recently. Who votes that I take away from 4s2 first? And that is the correct option. We're going to take 2 electrons here because 4 is the higher principal quantum number. As we add electrons to orbitals, especially in this location, 4s and 3d orbitals have very similar energy levels. We fill up the 4s, and then we fill up the 3d, and that's filling from lowest to highest energy. But you know what happens when that 4s is full and the 3d is empty? They actually shift energy changes, or shift energy levels. So when we go to remove electrons, it's now the 4s that has a higher energy than the 3d. So we fill it this way, 4s and then 3d, but as they get filled, the energy shifts, which means we always pull from the higher principal quantum number. I need to pull 3 electrons. I've taken 2 away from the highest principal quantum number, so the remaining I'm going to pull from my 3d. So that leaves me with 2 electrons hanging out in my 3d orbitals. Let's do one more example here. Gallium. Find it on your periodic table. We know how to write the neutral atom electron configuration already. Since argon, we've added 4s2, 3d10, and 4e1. But I want to make gallium 3+. To do that, I'm going to have to steal 3 electrons away. Okay, I'm going to start with the first electron that I want to steal. We're going to vote for 4s, 3d, or 4p. Where do I steal the first electron? Who votes for 4s? Who votes for 3d? Who votes for 4p? And that is correct. We're going to steal the first one here. We have 4s and 4p as the highest principal quantum number. When we compare s and p, p always has higher energy for the same principal quantum number. That means I'm going to steal my next 2 from the remaining highest principal quantum number. So the second and third electrons get stolen from there. That leaves me with argon and 3d10 electrons. Okay, well done. When we come back next class, I'm going to ask you to solve for manganese, and then we're going to wrap up our final topic in 2.1. Have a great weekend. Do those practice problems, and I'll see you on Monday.